Okay, first one, we have an aldehyde ketone, we have a diol, acid catalyst. Looks like a acetal, cyclic acetal. 3 carbons between the oxygens, 1, 2, 3. Cyclic acetal. You don't have to put the water. Major product. Major product is your acetal. How do we do? Amine, aldehyde ketone is going to be make it imine. Nitrogen replaces the oxygen. Sodium cyanoborohydride reduces the imine to the amine. So you end up with an H here and an H here. H there, you see that H there? Basically, we alkylated the amine. The original amine has 1 alkyl group, now it has 2. Reductive amination, how do we do? Make Grignard from the aryl bromide from a benzene. Grignard, essentially a benzene minus. Add the nitrile. Add the nitrile electrons here. You get this. If you throw in acid, you'll protonate that. Make the imine with an H. But this is aqueous. And with water, the imine will be hydrolyzed to the aldehyde ketone. So we make that ketone there. The name of that ketone is what? 1, 2, 3, 1, 2, 3, 4. It's actually a 1-phenyl, 1-butanone. That's interesting. You can actually have a ketone with the carbonyl at the 1 position. I think early on I said you could not, but that's 1 position because you don't count that ring. That's a substituent. 1-phenyl, 1-butanone. Basically enamine. Y'all remember enamine? Protonated carbonyl, we've been doing that for a good while. Nucleophile adds to protonated carbonyl, we've been doing that for a good while. Here we got to eliminate water. Proton transfer can give us a protonated oxygen. Then anytime we can make a lone pair, anytime we can make a pi bond using a lone pair, easy to do. We get to this point, that's got a positive charge. This cannot lose an H to go neutral, so instead we lose an H from the adjacent carbon. Take the H, electrons move in, these move back over here to get the enamine. Variety of resonance structures you could show here. Not a variety, I mean you could show the alternative resonance structure plus here and then you eliminate enamine mechanism. How do we do? Cyanohydrin of cyclobutanone. There you go. How do we do? Okay. I'll be posted upstairs. We're moving down the home stretch. And here they come. Kentucky Derby coming up soon, right? What's that? All right. Purple. Alpha carbonyl. Alpha carbonyl is acidic. We can do chemistry. What type of chemistry? You need to know enols. Enols, enolates. Enols are not favored. At equilibrium, ketone form is favored. Enol is a tautomer. Definition of a tautomer. Can be catalyzed by H plus or hydroxide. Either mechanism can be remembered by the mnemonic Oreo. Any questions about that up there? Questions? I would have thought there had been plenty of questions about all that. Well, which of the following are enol forms of the compound in the box? Yeah, the first two. Any questions about that?
One question. To show how to get the second one?
How do you get the second one?
Yeah.
What do you mean, how do you get it? Mechanistically?
Yeah.
Oreo should be able to do it. You talking about mechanism, Mark? Mm-hmm. It's the same way you get the other one, except you just remove a different H. Here you lose an H over here. I recommend you do mechanism for both and see how you get it. You know, really, this question, you don't even need the compound in the box. I mean, you kind of do. I mean, obviously, these are not even enols, right? What's an enol? Is an ene with an ol? That's an ene, but that ene not got an ol. Right? An enol is an alkene with an OH on the alkene carbons. Okay? How do we know both of these are enols of the compound in the box? Well, what's the definition of an enol is a tautomer. What's the definition of a tautomer? We're really looking for enol tautomers of the compound in the box. What's the definition of a tautomer? Okay. Most likely enol form here, what would it be? See that there? Enol, right? Enol. In this particular case, the enol is favored. That's unusual. Why is the enol favored? Peter? Because it's aromatic. It's a nice reason to prefer that structure. Aromatic, that's a phenol ring. Aromatic, as this structure, it's aromatic. 2, 4, 6 pi electrons here. The aromaticity is going to make this structure more stable than this one. Where usually the ketone form is more stable. Sometimes there's reasons why enols might be favored. Aromaticity. On the back side, that idea is pretty much repeated. Are these two tautomers? What's the definition of a tautomer? I won't ask that anymore. Need to know the definition of a tautomer. Okay. These tautomers here, which one's favored, keto or the enol? Yes, enol. Why? I mean, it's aromatic. That's phenol. Phenol exists that way. Actually, if you just look at that, that's enol. I mean, you could draw it as the keto form, but the enol is highly favored here. It's aromatic. Sometimes enols are favored. A little more difficult one over here. Not just a different idea. This is a 1,3 diketone. If that's 1, that's 3. Or sometimes I call it a beta diketone, because if that's alpha, that's beta. From here, the beta has another ketone, beta ketone, beta diketone. This actually prefers to exist like this, with one as a ketone, the other as the enol. Why does it prefer to exist like this? Somebody said it. Both of you said it. Here's the answers. You hear them? Conjugated. Here you have two different pi systems. Double bond, not conjugated. Totally separated. But here, what do you have? Now your double bonds are conjugated. Is conjugation better or not good? Better. The enol is conjugated. It's kind of like over here, enols aromatic, but here it's conjugated. It's conjugated all the way through here. Why did I include the oxygen? Because the lone pairs are conjugated all the way through there. Okay? Conjugation. What's the other reason, Chelsea?
Hydrogen bonding.
Hydrogen bonding is the other reason. Because I drew this right here so you can see it. You see that interaction between the H that's on an oxygen or N or F and the lone pair that's on an oxygen? That's an internal hydrogen bond. Intramolecular H bond. More bonding is good. Now it's not a covalent bond, but a hydrogen bond is worth about 10% of a covalent bond in terms of stability. Two reasons why that is the favorable. We could show this enol. That is an enol of this also. Why is this better than that one? I mean, you can hydrogen bond, but it's not conjugated. That's the preferred enol. Conjugated, hydrogen bond, and conjugated. If we got time, is it in this packet? No, I think it's in the other packet with the miscellaneous things, covers sort of both sections. Let's pull that packet out. Aldehyde ketone warm up, white. Yeah, there's a number of miscellaneous things in here. Actually, I might have taken it out. I didn't want it to be so much. I didn't realize I referred to it in the handout. Is there another miscellaneous handout? I don't think so. I must have taken that one out. If you want to look up those structures there, those drugs, those all contain stable enols. You might look up those compounds on the wiki and see why they're stable as enol form. Okay. Well, let's start doing chemistry at the alpha position. Alpha substitution reaction. We'll either replace an H with something or we'll replace the leaving group with something. First thing is replace an H with something. First thing we'll do is alpha halogenation. We can put a halogen at the alpha position. For example, you take acetophenone with this alpha position here, you can react it with bromine and an acid catalyst. Your choice, acetic acid. HBr is also kind of common to have the same anion as produced here. These are catalysts. We can get alpha bromination. What's the byproduct here? Plus what? Forget about the catalyst. What's the byproduct? If you react that with bromine, you get that plus what? HBr. It's nothing but just atom economy. You got to have another Br and you got to have an H. Most likely there's going to be HBr. That's not the same HBr here. That's a new HBr, full equivalent that's produced here. That's the fate of the other bromine, right? Okay. Mechanism for this. What do you want to do first? We're under acidic conditions. Do you want to protonate first? Okay. Here's your H plus catalyst. H plus and acetate minus or Br minus, either way. Let's protonate first. I'm going to get there. I'm going to jump ahead. Key intermediate. We may show it, we may not. We've already showed it. The key intermediate is, guess what? What's the donkey say?
No.
Enol. That's your key intermediate. How does this get to enol? We did that last time. It's over here. It's the same thing. It's the same exact compound. H plus catalyst or hydroxide. We're doing it with an H plus catalyst. HBr, acetic acid. You get that? Didn't we do this mechanism? The mechanism can be remembered by what mnemonic? Oreo. Okay, we've already done that. So I'm actually not going to repeat the mechanism. What was it? How many steps to this mechanism? Well, you got to be careful. It's 3 steps on the board, but one of them ain't really a step. Which one ain't really a step? Resonance ain't really a step. When we go from one structure to another, and they call it a step on the board, it's not really a step. I mean, we make pink. We just show red and white. Going from red to white is not a step when you're looking at pink. Okay. But Oreo makes it sound like 3 steps. Okay, there's your there. Your enol is your main intermediate. Okay, now we got a double bond here. Have you ever reacted a double bond with? Where are we at?
You're on the other side. Turn it over.
Where are we at?
There you go.
Okay. We're reacting with bromine. Forget about all this. Have you ever reacted a double bond with bromine? Okay, it's one of the first alkene reactions we did. I know my guys reacted an alkene with bromine in organic 1. Most likely all of you do. How do you react an alkene with bromine? That's all it is. Okay? Now usually if you take an isolated alkene, react with bromine, what do you get? I mean, if you react this, you get what? Let's do it with a ring because you can show the stereochemistry better with a ring, right? If you have cyclohexene reacted with bromine, what do you get? You get dibromide, vicinal dibromide, trans, right? Bromonium ion, backside attack, okay? Well, I'll just show this for completeness. If you take this and put an OH there, alkene, this is not just an old alkene, is it? That's now an enol. If you react this with bromine, you may think you get this with just an OH there. But instead you get ketone Br plus HBr. Ketone Br. Now, since I'm over here, I'm going to kind of just show you something, then we'll go over there and we'll do the mechanism, okay? This is free information, okay? Let's say there was no OH here. If we put the OH here, let's just put it there. It would be bold, right? I mean, we could show that as the product, but the problem is, anytime you can make pi bond, kick off a leaving group, that's easy to do. So this comes in and kicks that off. And what does that give? It gives double bond with an H, and then you got this Br over here. And then how do you get to that? Well, the Br that got kicked off takes that H, and you get that plus there you go. So it all migrates towards that product. Because that's not a stable carbon there, because anytime you make a pi bond kick off a leaving group, that's going to go back to the ketone, to carbonyl form. Now, when we do the mechanism, we may not show this exact structure. Because you can get there without first showing this. Let's do it over here. A different way. Here's your double bond, here's your bromine. Now when I taught this, I said, okay, this attacks. Are we going to leave plus on left or right?
Left.
Correct, left. Why? So these electrons pull away, attack the bromine, this leaves, and we get, I'm going to call this phenyl. We now attack bromine, plus charge here, with an OH, plus Br minus. Now in organic 1, what did we do here when we were doing a bromine addition to an alkene?
Bromine attacks again.
Back bond. We back bonded here, and we made what? It was called what? Called a bromonium ion, right? And we said that this was not actually formed. Remember all that? Okay, well in this case, it is formed, and you don't get back bonding. Because it says a bromine back bonding and supplying electrons to the cation, do we have something else that can supply electrons to the cation? Instead of this coming in, because that bromine really don't want to share its electrons. It's a greedy little something. And it don't want to strain to make this three-membered ring unless it has to in organic 1. Is there something else that can supply electrons here? How about this guy? And just move these down. And that gives what? Double bond with an H. That's a resonance structure. Double-headed resonance arrow. And there you go. There's your product. What do we need to do? Then that Br minus that got kicked off takes the H, and you get there. We did that step over here. See, it took the H. Except over here, I showed you like the Br, this Br ending up here. They probably don't end up there. Because the electrons from that oxygen move in so quick. In fact, they don't move in quick at all. They always are there, but that's resonance. You can't say that's super quick. It's like, no. As soon as this is formed, it's already there. I mean, these two exist. This is just, that's one structure. Okay? Because of that oxygen there moving in, that's how you get your ketone instead of a dibromide. That's your product. The key intermediate is your enol. Double bond, reactive bromine. You just have a little twist. Okay, that can be catalyzed by a variety of acids. I showed you common ones there. It could be a variety of things. We could do this with chlorine. Example down here. Okay? As practice, just do the mechanism. It's the same mechanism as above. You just got chlorine instead of bromine. It's just a different start material. Here's a little interesting thing. You actually do not have to use acid catalyst. Because the reaction is autocatalytic. What does autocatalytic mean? It catalyzes itself. This reaction, if you just add chlorine to this, you'll get that over there. It'll start slow at first. It'll be very slow at first. You may even think, well, how does it even react at first? Well, let's don't get into this. But I mean, any aldehyde ketone, there's a little bit of enol in there at equilibrium, 0.001%. Okay? And when this reacts with chlorine, it makes that plus what? Plus what? HCl. it makes HCl, what does the HCl, what can it now do? This starts serving as a catalyst. It generates its own catalyst once it gets going. That's called autocatalytic. And once it gets going, it'll speed up. We've actually done these reactions in the research lab with bromine. You add the bromine and it's real slow, and it kind of, is it reacting? Is it reacting? And then all of a sudden it reacts fast. Because the HBr built up and it's just kind of kicked in and catalyzed itself. Autocatalytic. Okay. You can also do these reactions under basic conditions. If you take such a outright a ketone. By the way, most of the examples here will be ketones. It's actually very difficult to do alpha chemistry with aldehydes because they're very reactive in other ways. So most of the example here is ketones. Take this ketone, chlorine excess. You know what excess is? Everybody know excess, right? It's abbreviation for excess. Sodium hydroxide, basic conditions. We can put 2 chlorines on, and we make what? 2 sodium chlorides. I see a lot of students see this and say, okay, 2 chlorines, there's your 2 chlorines. How many equivalents of chlorine do you need to do here? I said excess, but how many do you really need to do to make that? You need 2 equivalents to make that. 2 chlorines end up on your compound, 2 chlorines end up with sodium chloride. Just like before, okay? Under basic conditions, the key intermediate is not the enol, but the enolate. Here we have hydroxide. First thing happens is this takes an H. Make the carbanion. What's the name of this anion? Enolate. Why is it called enolate? Well, look at the resonance structure. If you do resonance, there's your enolate. Enol is the anion of enolate. Which is the measured resonance structure? That or this? Basically, the whole thing is called enolate. That's one structure, right? That's your enolate. Which one's major? This one, -1 oxygen. Okay? So somebody calling this enolate, you just got to know that, you know, they're referring to this resonance structure. Neither one is correct. Now we have a nucleophile here. That can be a nucleophile, this can be a nucleophile. With enolates, the oxygen is rarely ever, never nucleophile, especially in this class. It usually always reacts on carbon. There may be some special cases where this could react and this could attack something. But usually this attacks something. What does it attack in this reaction? Chlorine. And these electrons attack chlorine, electrons off. What do you get? You get that right there. Actually, the enolate reactions are much easier. All it is just remove proton, and then you do your reaction. If you look back at the previous mechanism when we had enol, enol did not have an anion. the double bond had to react as the nucleophile. But here we have an anion that can react as a classical nucleophile in here. What do? We just repeat the reaction. You just come in here with hydroxide, take the H, you make the anion again, now you react this with what? The other equivalent of chlorine, and you get your final product. We get sodium chloride, right? Because there's a sodium plus here. There's a sodium plus here, right? And there's also a Cl minus here. And we also have we generate a Cl minus here to go with that sodium plus that was there, that was here. So if you look at everything, sodium chloride is also formed. Hopefully this looks pretty straightforward. You make enolate carbanion, and the carbanion attacks your halogen. Exhaustive. Exhaustive means we do this until you can't do it anymore. Does that have another H to remove? There's no H remaining. Game over. You can't remove another H and do it again. Now it's actually hard to stop here. You may ask, can we just put one chlorine on? Hard to stop here. Under acidic conditions, you can stop there. Under basic conditions, you pretty much have to do exhaustive. Put all the halogens on that you can. You try to stop here, you'll get a mixture of this and that. And it won't be a good reaction. Mark?
Can you use the beta hydrogens?
You mean here?
Yeah.
Well, those aren't acidic.
Because they're not near the
So the anion would not be resonance stabilized. Why are all these acidic? Because resonance. Okay? We're doing alpha carbonyl chemistry, not beta. Why are we able to do alpha? Because the H's alpha to the carbonyl are acidic enough that we can remove and do chemistry with. And that's what we're doing over here. Why is it hard to stop there? Because which is more acidic, the starting material or this product here? Which is more acidic? Well, which is more stable? This carbanion or this carbanion? That carbanion you can do resonance with. You can also do resonance here. What else does this have going for it? You've also got the chlorine stabilizing it. This is a more stable carbanion. That's more acidic. So your product is more acidic. So as this reaction is happening, this has to do this a gazillion times. And say it's gone 10%, and you've got 10% of this sitting here. This base is going to take the most acidic proton around. It's going to say, "Oh, I'm liking this guy better." It will stop deprotonating that one and start deprotonating the more acidic one, and you'll put 2 on while that guy has none on. And if you only use one equivalent of chlorine, you'll end up with sort of a mixture here. You have to drive it all the way because of that problem, exhaustively. Under basic conditions, you put as many halogens on as you can at the alpha position by deprotonating and then halogenating. Under acidic conditions, you can put 1 on, like we did previously. So, what's the product of this reaction here? Mark, that was a good question. Questions like that are important because if you're thinking something, we can clarify it. I'm sure everybody can learn from it. Okay? The questions of why something else can't happen are good. Okay? I could talk about 2 weeks about that reaction. We don't have time. If you can tell me what you want to know, I can tell you what you need to know. Okay, product of this reaction. Exhaustive halogenation has the acidic CHs alpha to the carbonyl. There are 3 acidic H's, right? There's 1 there, and there's 2 there. We got both sides of the carbonyl here have H's. All 3 are acidic enough to be deprotonated, and then the carbanion attacks the bromine. How we do? Did you forget about one side? Chris? Which side did you forget about?
Left side.
There's an H there.
Yep.
Hydroxide, you can take it, because that's going to be an enolate. pK is 20, okay? Exhaustive. Haloform reaction. This is a unique reaction that involves exhaustive, but we get a quite different product over there, carboxylic acid. If you react a methyl ketone, with halogen and excess base, excess all this, we do that next week. You'll actually get a carboxylic acid plus that little guy, HX with 3 halogens. The first thing is exhaustive halogenation. And what does that give? What do you want to call this? Chlorine? That would give what? A carbon with 3 chlorines. Right? That's just deprotonate, chlorinate, deprotonate, chlorinate, deprotonate, chlorinate. 3 times. Exhaustive. Problem is the reaction doesn't stop here when you have 3 halogens on your alpha carbon. You only get 3 halogens when you start with what? A methyl ketone. Because this, we also have excess hydroxide. And we're out of time. Please finish up this mechanism and show how you get that product. Something else happens here. But guys, please also look ahead because we're going to have to pick up the pace a little bit. I'm going to assume that you've looked ahead, you've formed questions, and you're ready to hear my version of it. Math Day, Vidic, group, somebody got a group name? I think it says 3 to 4, whatever it says. See somebody in the lab today? Anybody interested in money? Okay. Try to do 2 scholarships this semester. We only have 1 applicant. About $17,000 a year. If you're interested in teaching this career, please see me.
Colonies easily. And
There's been about 15 students going through the program. Very successful.
oh, another winner.
I have a question. On the secondary, can you me making deforming the document? Can the